Okay, let's unpack this. Have you ever found yourself, really impressed by what large language models can do, but also maybe sometimes a bit frustrated by their speed or how they generate text, like one word after another? It's sort of like watching a painter work, stroke by painstaking stroke. You almost wish they could just splash the whole masterpiece onto the canvas at once. Well, today we're doing a deep dive into a really revolutionary approach that's challenging exactly that. Diffusion language models. DLMs. Imagine an AI that doesn't just predict the next word. Instead, it sketches out maybe an entire sentence or paragraph and then refines it over and over until it's, well, perfect. That's the core promise here, and honestly, it's a pretty big one.
Exactly. And what's got us buzzing today is this comprehensive survey, a survey on diffusion language models. This isn't just, another academic paper. It's more like a roadmap. It shows this landscape that's evolving incredibly fast. So our mission for you today is to really cut through the technical jargon. We want to reveal the key insights, those aha moments that show why DLMs aren't just some alternative. They're a compelling, maybe even game-changing approach to how AI understands and generates language.
Right. And the why really starts with the fundamental bottleneck, doesn't it? We're all blown away by models like GPT. Yeah. But here's where it gets really interesting. They're one token at a time thing, that autoregressive generation. It's powerful, sure, but it creates a major speed bump. It's like building a wall one brick at a time. Perfect bricks, maybe, but slow. That sequential nature inherently limits their inference speed, their throughput. It's a big challenge. And it's one that DLMs are basically designed to smash.
That's precisely the problem they're aiming to solve. And it's funny, the origin story for diffusion models actually started with images and video. Think about the magic behind Stable Diffusion, or Imagen, or Sora. Incredible stuff. Their core concept is really quite elegant. You start with completely noisy data, like imagine a totally scrambled image. And through this progressive denoising process, the model iteratively recovers the original clear data. It's kind of like watching a blurry photo slowly snap into perfect focus layer by layer.
Okay, so how does that visual magic translate to something abstract like language? That seems like a big leap. Instead of pixels, you're saying apply that same iterative refinement idea to text. That's the fundamental idea with DLMs, generating tokens in parallel through this iterative denoising. You start with maybe a masked sequence, almost gibberish, right? And the model refines it step by step, filling in the blanks, making it coherent. It's a completely different way of building sentences compared to just predicting word after word.
And connecting this back to the bigger picture, one of the most compelling advantages, as you hinted, is just sheer speed. Because DLMs can generate multiple tokens at the same time, not one after another. Well, this is huge for efficiency. It significantly improves inference speed and throughput compared to those traditional autoregressive models. It directly tackles that bottleneck we mentioned earlier.
Speed is obviously great, but it's not the only story here, is it? Think about how you understand a sentence. You get a word better if you know what comes before it and what comes after it. DLMs inherently do this. They naturally incorporate bidirectional context during generation. And that allows for really fine-grained control, a more nuanced understanding, often produces richer text, more aware of the context.
Yeah, and another really fascinating aspect is that iterative refinement process itself. The whole denoising thing lets DLMs continually update and improve their output over multiple steps. They can accept high-confidence tokens early on, but keep the uncertain parts masked. This lets them progressively refine those trickier areas. It often leads to text that feels more coherent, higher quality than you might get from a single pass. It's almost like having a built-in editor that's constantly making improvements.
Exactly, like a self-correction mechanism or progressive shaping.
Yeah.
Plus the controllability.
Yeah.
That's a massive advantage too. You can condition DLMs on specific token positions or structures really precisely. That makes them incredibly well-suited for tasks like filling in missing parts of text smoothly, or generating text in a very specific style or tone. You can guide them with a much firmer hand, it seems.
Which brings us to a pretty crucial point: how these models handle different types of data. Because they share this denoising-based framework, DLMs are naturally quite suited for unified text and vision generation tasks. This multimodal capability is a really significant draw. It allows a single model to both understand and generate across different data types, like describing an image or creating an image from a text prompt.
Okay, so when DLMs were first getting started, researchers explored a couple of main paths, right? You had these continuous DLMs. They basically mapped the discrete language tokens into a continuous sort of numerical space, an embedding space. And then they did their denoising magic there, kind of blurring the lines between words to work in more flexible space. Models like Diffusion LM were pioneers there.
And then came discrete DLMs. These define the diffusion process directly in the token space itself. often by like masking out parts of a sequence and learning to fill them back in. D3PM was an early example. What's really insightful from the survey, though, is that while the continuous models came first, there's a really clear trend now of discrete DLMs gaining popularity, which tells us a lot, I think, about the practical breakthroughs needed to handle language directly rather than abstracting it away first.
And this innovation is leading to some genuinely remarkable results. I mean, Elevili 8b, Dream 7b. These aren't just technical names, are they? They're pivotal because they showed really for the first time that DLMs could match or even beat established AR models of a similar size, like LFME3 8b. This wasn't just quick development. It was proof that DLMs are viable, serious contenders, not just a neat trick. And we're also seeing these powerful multimodal DLMs emerging, like LFE Dimple, MADA, showing incredible promise for tasks that mix text and images.
So digging a bit deeper, how are these powerful models actually trained? The survey outlines a few key strategies. Some are pre-trained completely from scratch, building their knowledge base right from the ground up. LD A8B is like that. But to speed things up, a lot of models think Dream or Diffulama actually adapt from existing autoregressive models, gives them a head start, basically. And fascinatingly, in the multimodal world, we're even seeing adaptation from image diffusion models like DDIT, sort of bridging vision and language from the other side.
Okay, and what about supervised fine-tuning, SFT? Is that similar to AR models? For these masked DLMs, it seems like prompt tokens are usually left unmasked, and the model learns conditional generation by selectively masking the response tokens it needs to predict. But this raises a really crucial question, one this survey digs into. How do you get a parallel generator to do complex step-by-step reasoning? Traditional chain of thought reasoning relies heavily on that one token at a time output, doesn't it? Trying to get a DLM to do that feels like trying to parallel park a train.
It is a unique challenge, a formidable one, actually, precisely because the way DLMs generate makes applying standard reinforcement learning really hard. Those methods often rely on easily calculating a probability of a specific output sequence, which is tricky for DLMs. But researchers are finding some clever ways around it. You have methods like diffusion of thought, or DOT. It sort of adapts chain of thought by refining intermediate thoughts in parallel. And then there's diffusion chain of lateral thought, DOCT. That uses outcome-based RL to optimize the whole multi-step denoising path. It even learns the best order to reveal tokens. Essentially, they're adapting advanced RL techniques specifically for the DLM process, optimizing the whole trajectory, not just single predictions.
Okay, so once they're trained, how do we make them perform at their absolute best during inference? That's key, right? It's not just about generating in parallel. It's about doing it smartly. For instance, you mentioned models like FastDLLM using confidence-aware decoding. So they only unmask tokens they're pretty sure about. That sounds like it could give a good speed up without losing too much quality. There are other techniques, like speculative diffusion decoding, where a small DLM drafts something quickly and a big AR model checks it, combining strengths.
Exactly. And that iterative refinement idea also shows up in specific unmasking and remasking strategies. High-confidence tokens get revealed quickly, but uncertain ones stay masked for more work. Models like LADA and Dream do this. Some advanced methods, like RAMDM, can even remask tokens that were already decoded if the model's confidence drops. It allows for a smoother trade-off between computation time and the final output quality.
And if you want to steer the generation, like for a specific style or tone, that's where guidance comes in. Techniques like classifier-free guidance, CFG, you hear about that a lot with image models are used here too. They basically direct the DLM's output towards certain attributes or conditions. Think of it like gently nudging the model, keeping it on topic, or within a specific creative boundary.
Definitely. And on the pure efficiency side, DLMs are adapting some clever tricks and inventing new ones too. Key value caching, or KV caching, that's a really common optimization in AR models. Well, it's being adapted for DLMs too, through things like blockwise diffusion or delayed caching. Even with their bidirectional nature, this helps reuse computations across the model, making things faster.
Right, and it gets even more granular with something called feature caching. So caching intermediate activations during the denoising steps to avoid recalculating stuff.
It avoids redundant computation, can give significant speedups. Deep Cache pioneered this, and now approaches like DLLM cache are adapting it specifically for text. They cache the queen tokens and only refresh the dynamic position still being refined. Pretty smart.
Wow. And then there's step distillation. That sounds potentially transformative.
It really is. This technique essentially collapses many denoising steps into just a few, or maybe even a single step. It drastically cuts down inference time, though there's an initial training cost to do the distillation. Models like DLM-1, for example, can generate an entire sequence in just one forward pass. Massive acceleration, super fast text generation.
So these innovations aren't just theoretical concepts. They're finding real-world applications, way beyond just general text. We touched on the multimodal models earlier, like LADV, which uses vision for instruction tuning, so the model can respond to instructions that mix text and images.
Yeah, and MD offers unified multimodal understanding and generation. It uses a technique called VQVAE to represent images discretely. That helps bridge the gap between visual information and language.
And they're being used in conventional NLP tasks, too.
Oh, yes, they're proving quite effective. We're seeing them applied to text classification, like with ROICDM. Even complex tasks like named entity recognition diffusioners tackling that. Their iterative nature seems good for machine translation, too. XDLM is doing cross-lingual pre-training for diffusion models. So it's not just about generating new text, but also understanding and transforming existing text.
Okay, this one's really interesting. Code generation. Why are DLMs surprisingly good for code?
It seems their iterative refinement and sort of global planning capabilities are a great fit. Code often has this non-sequential structured nature, right? DLMs can refine syntax and logic across a whole block. Models like Diffucoder, that's an open source 7B model, and Mercury Coder, which boasts incredible speed, are showing this. They seem to produce more robust, more correct code sometimes.
And that iterative design principle even extends into science, biology. That's fascinating.
It really is. We're seeing some intriguing uses in computational biology. Things like text-guided molecular optimization, trans-DLM, TGM-DLM are examples. And for protein design, models like ForceGen and DPLM are generating sequences to meet specific complex functional goals. It really makes you wonder, doesn't it? Can DLMs accelerate discovery in fields where iterative design is just fundamental?
Okay, this all sounds incredibly promising, but it wouldn't be a proper deep dive if we didn't look at the road ahead, the challenges. And there's a big one. Let's unpack this. The parallelism performance trade-off, sometimes called the parallel decoding curse. Like, imagine you're trying to guess a sequence, say ABAB. An AR model guesses A, then B, then A, builds it coherently, step by step. A DLM trying to guess all at once, especially if you reduce the denoising steps to make it faster, it might see A and B as equally likely at every position, and it could end up with junk like AABA. This parallel decoding curse is a huge challenge for maintaining fluency, consistency, especially when you push for speed.
That's a critical point for quality, absolutely. And beyond that, there's a significant infrastructure challenge. Compared to the really mature ecosystem around autoregressive models, well, DLMs lack optimized open source libraries and deployment frameworks. There's no equivalent to something like VLM for efficient serving right now. And that can be a real barrier for researchers, for developers trying to actually use and deploy these models.
They also seem to struggle currently with very long sequences or dynamic length generation.
Yeah, most DLMs are trained for fixed length outputs. Generalizing to really long text or unpredictable lengths is hard. And because they use that full bidirectional attention at every denoising step, the computational costs can balloon. Without serious optimizations, it can scale really poorly, something like ON3, which limits handling truly long sequences.
And finally, just sheer scale.
Scalability is still an underexplored challenge, yeah. The largest publicly available DLMs are around, 8 billion parameters, which is incredibly powerful for that size. But it's significantly smaller than the leading AR models' hundreds of billions, even trillions of parameters. While models like Mercury and Gemini Diffusion show promise, they still generally fall short of the absolute state-of-the-art AR models across the board in terms of raw scale.
Right. But despite these hurdles, the future directions look incredibly promising. And that's what's really exciting here. We're seeing active research into better training efficiency, using tokens more effectively, innovative model compression, quantization, distillation to get faster, smaller models. There's huge potential in pushing for truly unified multimodal reasoning, beyond just generating text and images, but really understanding the interplay. And maybe the most intriguing, developing DLM-based agents, using their unique abilities for flexible, adaptive AI agents that can plan and refine actions iteratively. So what does this all mean for you listening? It means this field is wide open, incredible potential to tackle some of the biggest AI hurdles today, moving us closer to genuinely intelligent, versatile systems.
Which really raises an important question, doesn't it? If diffusion language models can eventually reach the scale and fluency of AR models, but they keep their inherent advantages in speed, control, multimodal skills, what kinds of entirely new applications, new interactions might they unlock? things we can't even really imagine with today's tech. Think beyond just chatbots and image generators. What about new forms of creative AI or scientific discovery?
It really makes you wonder, doesn't it? Are we witnessing this quiet revolution? One that could redefine how we build and interact with AI in the future. Definitely something to chew on until our next deep dive.